So last time we developed some stress-strain relations, and now we're going to take those and reduce them down to plane stress, which is, of course, most of the problems that we're going to look at. So if you remember here, the stress-strain relations that we came up with for orthotropic material, remember we said we could use these interchangeably because the matrix is symmetric. And now we're going to, again, look at a case of plane stress. And so for plane stress, of course, what that means is that those out-of-plane stresses, sigma 3, tau 2, 3, and tau 1, 3 are all equal to 0. So we can knock those out. If we set those all to 0, then of course it doesn't matter what we multiply those, so we can get rid of these three columns. And we're not really interested in what the out-of-plane strains are, and so we can knock those out as well, which means we can knock those rows out and end up with a 3 by 3 matrix that relates the strains to the stresses. Now, we'd like to be able to invert that, but let's talk about that for just a moment. Notice that we don't imply that the strain in the 3 direction is equal to 0. In fact, it's not. But it's not really of interest. Because of Poisson's ratios in general, if you pull in the one direction, it's going to reduce the thickness in the 3 direction. But again, that's not of interest to us. So what we want to do is invert that S matrix so that we have stress as a function of strain. And we call that matrix, once we've inverted the 3 by 3, we call that the Q, or the reduced stiffness matrix. So kind of notice here what we did was we started with the compliance matrix and knocked out rows and columns. We did that because it's under a state of plane stress. We cannot start with the stiffness matrix, the C matrix, and do the same thing because that would imply that it's plane strain and not plane stress. So again, it may seem like not that big of a deal, but yeah, it really is that the plate and shells theory is based on it being a state of plane stress and not of plane strain. So again, we would call the 6 by 6 and the 3 by 3 compliance matrix, we'll call those S for both. But because of the fact that the stiffness matrix is different for a 3 by 3, a plane stress, we give it the designation Q. And so C if it's the 6 by 6, Q if it's the 3 by 3 for plane stress. Okay. So again, we can find the components of that by inverting the 3 by 3 S matrix. And by the way, you did notice that we don't say it's 1, 3, 2, 3, and 3, 3. We say that we use 6 for the last column and last row because remember we've eliminated rows and columns 3 to 5. So again, we can find those directly, but we're going to do that inverting the matrix. Rather than doing that, we're going to just find these directly. It's not that bad to do because of the zeros that are in there. What it amounts to is that the first two equations are not dependent at all on the third equation. And so I really only have to solve those two equations simultaneously. So here are those first two equations written out. And so when we combine those, one way to do it, and remember this relation between the Poisson's ratios here, if we substitute that into the first equation and then multiply the second equation through by nu 2, 1, and then add those together, we'll eliminate the sigma 2 term. And so here's what we have. Now we only have sigma 1, and then we have epsilon 1 and epsilon 2 still in the equation. So what we want to do is solve that for sigma 1. And so just rearranging this a little bit, gathering the sigma 1 terms, then we end up with this equation. So you can see these are going to be the Q11 and Q12 terms of that matrix. If we do a similar kind of thing, we come up with an equation for sigma 2. Okay. Now remember, the shear equation is uncoupled from the others, so it's very easy just to say, well, okay, the shear stress is 1 over g times the shear excuse me, the shear strain is 1 over g times the shear stress, so the shear stress is just g times the shear strain. And so there is the Q matrix, okay? And again, shorthand, we'll just say these local stresses are related to the local strains by the Q matrix. And remember this too, that the matrix is going to be symmetric because of the fact that nu12 times E2 is equal to nu21 times E1. So we can use either one of those formulations. It is a symmetric matrix. All right, well now I want to do the same thing, except now instead of local coordinates, I want to transform this to global coordinates. So starting with this equation and recognizing that we can use some of the transformation equations that we used earlier, we could start out by noticing that the local stresses, if we multiply by T1 inverse, and so again we have to multiply both sides by the T1 inverse matrix. Well, the T1 inverse matrix times the local stresses gives me the global stresses. And similarly, the local strains are equal to T2 times the global strains. So now what we have are the global stresses on the left, the global strains on the right, and so what's in between there we now call the Q bar matrix that has those transformed terms in it. And again, there's the definition of the Q bar matrix, T1 inverse times the Q matrix times T2. And now what I want to do, and I'll kind of go through this kind of quickly, but I want to show you how we can generate all of those terms. So let's write out, here's the T1 inverse matrix, there's the Q matrix, and we'll leave the T2 just as T2 for a moment, because the first thing we want to do is just multiply these two matrices together. So for example, the first term here would be m squared Q11 plus n squared Q12. And we do that for the entire 3 by 3 times a 3 by 3 gives us this 3 by 3, and then we multiply that by the T2 matrix. Okay. So let's start out by finding Q bar 1, 1. So we would take this first row times the first column and expand that out and kind of group some terms. And here's what we end up with for the Q bar 1, 1 term. By the way, these terms are all listed in your summary sheets. Similarly, if we want to do Q bar 1, 2, we take the first row times the second column, and again group the terms according to the sines and cosines here. Remember, cosine is m, sine is n. And now Q bar 1, 6, so the first row times the last column, which remember we said is we would designate as 6, and we end up with this expression right here. One thing to notice about this one is that there are odd powers of both the cosine and the sine, and we'll talk about why that's significant in just a little bit, whereas the 1, 1 and the 1, 2 terms both only had even powers. Okay, we won't do them all, but here's one. Let's do the 2, 1, second row times first column, and when we group all the terms from that, we'll see that Q bar 2, 1 is Q bar 1, 2. In other words, Q bar is going to be a symmetric matrix, even though it's logical but not obvious, because this matrix is not symmetric and this matrix is not symmetric, but the product of the two is going to be a symmetric matrix. And we'll just show you one more here. This will be the 6, 6 term. And there's the final result for that. So again, notice that there are even powers of both the sine and the cosine for this one. So the ones that we didn't go through, there's Q bar 2, 2, Q bar 2, 6, again similar forms to Q bar 1, 1 and Q bar 1, 6, and again symmetric matrix. And so again, all of the terms are listed in the summary sheets. So notice again, the Q bar matrix is symmetric. And also, as we notice, Q bar 1, 6, this should actually say Q bar 2, 6 right here. all the terms have even powers of the sign. And so what that means is that for all of those terms, the plus theta and the minus theta will have the same values. But for q bar 16 and q bar 26, with the odd powers, again, the sign is going to have either positive or negative. And so those, remember what those terms represent: extension, shear, coupling. So if we have equal amounts of a plus theta and minus theta material, those terms end up canceling each other out. So we call that a balanced laminate. So if you pull this in tension, say in the x direction, you won't get any in-plane shear as long as you're balanced, and these terms will cancel each other out. So what we'll do next time is we'll look through a numerical example where we'll look at a couple of different layers, apply a strain, and see what the stresses come out for those layers.